we're gonna talk about experimental design notes. We're gonna label. And we'll add some stuff here. And I'm gonna write various things to help you better understand, not necessarily the full definition, but when are you going to use it and how to identify it in a word problem. So let's start by being scientists about this. Okay. What can you measure?
Yes.
What about this? What I'm doing up here. What can you measure? Speak up. I can measure letting it drop to the ground. What actual measurement would that be?
Height.
Okay, the height I start, and the velocity, the speed, the time it takes to get from there down to there. All right, so the speed of the helicopter. What else? Yes?
Like where you, like the height of when you first started.
All right, we already said that. What else? Anything about this I can measure? The base of it. Raise your hand. Too many people talking at once. Yes?
How fast would it spin?
Okay, stop right there. Now you're talking about making a change to this. We're going to get to that. That's a change, right? Well, right now we haven't even defined any of these terms yet. We're just seeing what we can measure. So keep that on standby. What else? What about the helicopter? Yes. All right. We'll say mass. The mass of the helicopter. Yes.
The wingspan.
The wingspan. So like this, I can measure this. You said from the base. All right. That's all stuff we can measure. Now we have not done anything in the experimental design world other than identify this is a helicopter. Identify that's the ceiling. Okay. So I'm going to be enlisting your services later. All right. So here we go. That's the part you're going to go pick up. So, try one. Try two. I wouldn't say that. Try three. Okay. Every single one of those things were measurements from the starting point to the time, stopwatch or something, or doing, probably more accurate to measure that. Okay, Jacob, tell me what you said earlier.
If the spin, if it'll spin faster, if you cut the propeller.
Right, so he said if I cut the propeller, he's automatically implemented a change, something that we do, an intentional change. So I'm not going to do that because I want to use this, but that's something we could do. What am I doing now? I'm adding weight or I'm increasing the mass. And I could do it like this and have one paper clip, two paper clip, three, and that's called iterations, which we're going to explain in a second. So what I've done, without doing anything else, you've only seen the helicopter fly unaltered, right? So we need to, I don't know what that sound was, all right? So unaltered. Let's start here. Do you notice? I'm going to define some notes here, but I'm not going in order with the paper. There's a reason for that. Good science tries to identify problems, like how can I increase the speed of this helicopter or maximize the flight of this helicopter. Okay, so first thing, I'm going to underline things. You need to be writing this on your paper. Right, what is the variable? It's purposely changed. I'm going to give you 3 ways of identifying independent variable. 2 of them right now are on the paper. All right, purposely changed. Or I'm going to add in intentionally changed. That's a good buzzword. It's an intentional change. A manipulated change. A purposeful change. All right, does everyone have that? Okay. Now, let's talk here. Dependent variable. So look, this handout was designed as a guide for students to set up an experiment. Some of the stuff on here isn't the actual definition. It's more of like, hey, how should you do it? For example, if you look here, it says it's usually measures items. That's not defining dependent variable. That's saying what you would do to measure it. So this right here, that the response to the manipulated change, hey, we got another one. We got another EV. So manipulated change, that's another IV. The dependent variable is the response to the manipulated change. Everyone see that? The DV is the response to the manipulated change. It's something that can be measured. Independent variables measured, dependent variables measured. I'm going to skip down to control now, and then we'll do constant next. Okay? Control. You just saw me drop a helicopter, right? 3 times? Did you see me drop the helicopter with the intentional change yet? So, the control has data. It should be in a data table. You just saw trial 1, 2, and 3 of the control. So let's look at the notes. Is the standard for comparison? Yes. However, it doesn't say it anywhere in at this point in the notes, the basic definition. So let's do it. It is doing the experiment, or I'm just going to say doing W/O. What does that mean? W/O? Without. So don't use my abbreviations. Let me point this out. Throughout the year, there's going to be times where I'm going to write stuff up here, and it's not going to make any sense on your notes if you write the abbreviations if you're not used to using them. So write the full word. All right? For example, over here I wrote intentional. Maybe you should fit that in here, or make sure you know it goes with what you wrote for independent variable. So doing the experiment without the IV. Doing the experiment without the IV. That is your control. It should have numbers. It should have data. It should fit into a data table. Because we're doing this, we're trying to do the standard comparison. If the helicopter is going to increase or decrease from what? Compared to doing it without the paper clips added. Does that make sense? Okay. Now, let's go up to here. Hypothesis. A hypothesis, as this said, I said I'm not going to accept saying educated guess. I want a relationship between variables. It's focusing on the IV on the DV. It's a prediction about the IV and what it will do to the DV. Now, I'm going to write this over here. You guys probably just fit it on your notes. All right? I'm going to write this over here. Okay. Generically, it is a test. If you can read my bad handwriting. It's a testable question. All right? Now, we're not going to really focus saying if, then we'll use it. We're not going to say I. Get rid of the I. There's no first person. Okay? We'll say if the experimenter does, that's the IV, then the DV is going to respond. We're going to elaborate next class. Sure, I'm not hanging out with that. All right. What else? What about constants? Most important thing about the constant is that it remains the same and has a value. Okay. Remains the same and has a value. Let's look at what we just did. What of what we did before can be the constant? Please don't say the helicopter. That's the thing that you're experimenting on. Yes?
The height.
The height. Here's a rule of thumb. The most important constant is the one that could be a variable. Now you said change the wings. You know what we could do? We could not increase the mass, but change the distance. And now we're still talking about manipulations of helicopter flight. But we're doing, we say make the mass constant and then test different heights. If I did this, and then I dropped it from the ceiling, and then I dropped it from here, that's bad science. I need to, put a note, put it in your notes. The most important constant is one that could be a variable. See, that's the way you can do layered experiments where you have all these different things. Well, you guys, you're going to have that constant there, but for them, it's going to be a variable. And their variable is going to be a constant. So you can do a whole bunch of experiments. You set it up, you make your intentional change, and then you do one without the intentional change, so you have a control.
Remember, if the constant gives you a fixed value, you must put that down. Okay? For example, when I start out, It said the height was probably roughly about how high? About 8 feet, right? From the floor to the ceiling. So if that's given to you in the problem, we say, what is the most important constant? You can't just say height from ceiling to floor.
We'll take points off on a quiz or a test.
Although that is partially correct, that if they say it's 8 feet, you must say 8 feet from ceiling to floor. Make sense? You gotta include the fixed value.
So, as we've gone through here, we've talked about the constants. We have not tested this hypothesis. We have one. We made an intentional change. We increased the mass. So we'll do that in a second. And you notice repeat trials is every time the experiment is done, that counts as a trial. When we're going to do something later where we're going to have everyone work in groups. Each one of the group is doing the experiment. Each one of those groups counts as a trial. Even though they may have only done it once, the experiment needs to be done multiple times. So give me a hypothesis on this manipulated change, and we'll test it. It's going to fall faster. Say it better.
If the paper is being added to the paper helicopter, then the paper helicopter will hit the ground quicker.
Hit the ground quicker or go faster. Okay, which is what he said. All right. So we're basically saying this should go faster than it did without it. All right. My assistant should be ready. Ready? Try one.
Oh my god.
Where? Okay. Make a little adjustment.
Looks prettier.
All right. Can we make a conclusion?
Yes.
Yes.
The paperclip was added, so then that means that the thing went faster down.
Faster down to the floor. Okay. Or how about just a yes/no statement about the hypothesis?
Wait, yes, it did fall faster.
Okay. What's it?
Yes, the helicopter, the paper helicopter fell faster.
All right. Now it sounds like I'm being picky. It's because I'm being picky, but the whole idea is being able to communicate. What do we do as science? And then we write it up. Now, granted, you write it very formally if this was a lab report, but we have a conclusion.
Now, his hypothesis was by adding mass, the helicopter would fly faster. So what if we added mass and it actually went slower than without pixels? Although our hypothesis said it would go faster. Is that bad science?
No.
How many people think it's bad science? We didn't prove our hypothesis. Raise your hand. How many people think it's still good science even though we did not prove our hypothesis? It is still good science if you disprove your hypothesis. Your goal in the experiment is not to prove your hypothesis correct. Okay? Remember that. Because that's where all the problems in science get created, is when they're worried about the outcome proving the hypothesis correct, not just proving the facts correct. If it did not turn out the way we thought it would in our hypothesis, what do? We go back, we revise our hypothesis, and we test it again. That's good science. So if you don't prove your hypothesis, don't say, oh, this was all a failure. It was just as important to disprove it as it was to prove it. So don't get caught up in it's got to be right.
All right. There we go. That's experimental design. So let's work out.